So the talk is line segment tracking at the HL-LHC. Okay, so we all know that track finding at the HL-LHC is going to be quite difficult because there are going to be a lot of collisions and a lot more hits and a lot more ways to connect hits. So combinatorially, things are going to shoot up, and it will take around 100 times more time to reconstruct using the current methods that CMS uses. So which means we need to look at new stuff essentially. However, we can't just use single core CPUs anymore because single thread CPU performance is plateauing. And so we need to kind of move into new paradigms like GPUs and so on. So this is something that we saw earlier today about the tracker structure in the CMS. So we shall be focusing mostly on the outer track. We shall be focusing only on the outer tracker. So as we know, so we have this sort of bilayer tracker modules for phase 2 CMS. And as we saw in the previous talk, things that are kind of consistent with relatively high momentum pass through, and things that are not consistent fail. And so this will be kind of our fundamental building block for the algorithm. And our typical PT values would be something like greater than 0.8. Given that we are mostly dealing in with HLT tracking and offline tracking. So our algorithm itself is a bottom-up localized approach to track reconstruction. So it was first introduced in CTD2020. So what we do is we have these charged particle hits that are kind of clustered to create bigger and bigger track objects. And ultimately, we can reconstruct the entire tracks this way. Think of it as a kind of like building a kind of a tree from the ground up. So like two hits will be correlated to form a small track, and then two small tracks will then join to form a bigger track, and so on and so on. So essentially, every step can be parallelized, though the whole thing kind of runs in sequence. Like first you create all the small track stubs, and then you link all of them to create a slightly bigger track stub, and so on. And okay, so now let's kind of get into the sort of objects that we are going to deal with. So we call these sort of objects mini doublets. It's just created from two hits in a bilayer PT module. And so we only reconstruct those consistent with the track PT greater than 0.8 GeV. Then two mini doublets will link up to form what we call a line segment. So to jump from essentially one layer to another, instead of like iterating through the whole detector or like through all modules from one layer to another, we derived a map of valid module connections, a bunch of lookup tables basically that tell you from this particular module, only these many modules are kind of valid. And so this was derived from simulations and from kind of first principle saying helix of PT 0.8 GeV can only go to these many places from a given starting point. Then once we have these objects, we can kind of link them up further. So we have one segment here. We then link it up with another segment, and we have a criterion that one of these mini doublets need to be common. And so we create a triplet. Now this is 6 hits. Then what we can do is we can link up two triplets to form a quintuplet. And by now we've already covered 5 layers out of a 6-layer detector. And so to add things, and so one thing to notice out here is that we still haven't relied on the inner tracker yet, or the inner pixel tracker yet. So we can kind of use this object to reconstruct displaced tracks. Now, when we start relying on the inner tracker, the pixel tracker, we kind of incorporate it as a line segment. So we can create what's called a pixel triplet, that is essentially get one of these and find all triplets that are consistent with this. And so you can create a pixel line segment. And then finally, we can also do that with the same here. So we have a huge object here, and then we link it up with a pixel line segment to essentially form what we call a pixel quintuplet. So these will be quite pure because essentially this is kind of being the inner tracker here, seeding things out and capturing all these already very clean objects. So the pixel quintuplets would be quite clean. And then our final track candidate collection would be, of course, the pixel quintuplets, the pixel triplets, and these quintuplets. This is mainly for the displaced tracks. And we also use some unused pixel tracker seeds here, mainly to like boost up our efficiency, especially in the forward regions, mostly beyond 8 of 2.4. And to ensure there are no duplicates here, we do a duplicate cleaning in 8 space to ensure only like the most minimum set of objects that would completely reconstruct the efficiency are stored. So and then finally when of course now we go to the physics performance. So these were done using 200 events from TT bar plus pilot 200 sample. And we do standard track matching, which is if 75% of reconstructed hits matched to a simulated track, then we call it pass. And so this is the efficiency as a function of PT and efficiency as a function of theta. The efficiency saturates at 90%, which makes it competitive with existing CMS tracking algorithms for phase 2. And as we see, the turn on is only at 0.8 GeV, since only PT 0.8 GeV tracks are reconstructed. And so the most selling point of our algorithm is mostly the displaced track front, since we saw that we don't really fully rely on the pixel tracker, and we see a decent reconstruction efficiency for the displaced track. So these were this was measured in a sample of displaced neon tracks in a kind of a 5 centimeter cube around the interaction point. And however, we still can do it further. So this was kind of something we got for free, essentially. And if we work on this more, we can get this up. Then on the fake rate front, so most of these fakes out here, they come from the pixel. They mostly come from pixel seeds, because we're using a very dirty sample of pixel seeds. So other than that, on the data side, especially in the central region where our algorithm does its magic, our fake rates are quite consistent with the baseline. Okay, so this is on the physics front. So the main magic lies in kind of deploying this into GPUs and speeding things up, because as such, if you try to run this whole thing on a single thread CPU, it'll take at least 2 days to reconstruct an entire event. So the main magic comes from GPUs. So this is just kind of a 101 for GPUs. So in case of GPUs, there are a lot of compute cores, but they compromise on caches and data transport. So if you can make it such a way that the compute cores work on existing data while waiting for new data, you can essentially gain significant speedups. So the way we went around implementing it in the GPUs is that all these objects are kind of created in sequence. So all the mini doublets get created first, then the segments will use the information created by the mini doublets to create segments, and so on. So the object creation thing is sequential, but each of these blocks is parallelized. So for instance, when it comes to like quintuplets and so on, there are a lot of complicated selections involved. But then you can parallelize each of these steps in a GPU, essentially. And we store data in like this kind of a weird format called structure of arrays, where let's say a particular parameter for a particular object is stored in sequence instead of, say, for instance, if you want to store one particular parameter of the quintuplets, you just store all of them alone in sequence instead of, say, storing entire objects in sequence. This is mainly for efficient access on the GPU front. And turns out allocating memory in GPU has a lot of overhead. So we came up with some custom caching allocators that can speed things up quickly. And yeah, so this is kind of black magic here, which even we don't really understand. So this is multi-streaming. What we do in GPUs is GPUs can essentially run many kernels in parallel. So a kernel is essentially a compute unit that a GPU can run. With GPUs, you can kind of manage to run many kernels in parallel. So we mapped every stream to an event. So in that sense, what we can do is we can essentially run 8 pilot 200 events in parallel. But in our case, this is kind of, as you see here, it's kind of complicated because, so for instance, this one will be creating mini doublets from one event. And at the same time, the GPU will start doing something else for some other event in parallel. The moment it finds empty cores, it simply goes around assigning work with it. So the overall compute, compute throughput increases drastically in that case. It's like simply assigning work to empty workers whenever the workers get idle. So this whole thing the GPU does by itself. We don't really do much here. That's why I said this whole thing is kind of black magic to us. So what we learned over this process when it came to say implementing things on GPUs, this kind of we go into a little bit of nitty-gritty details here. As I told you, memory allocation has overheads. So we spend time writing a custom memory caching allocator that exponentially allocates memory. So for instance, if you want 2 MB, it gives you 2 MB. But then if you want 3 MB of space, it gives you 4 MB. And then if you want say 6 MB, let's say 5 MB, the custom caching allocator will give you 8 MB in return. So it's basically kind of exponential. So in that way, we were able to avoid reallocation costs, and it improved our timing by 25%. And earlier GPUs used to have this thing called thread divergence. So GPUs are kind of designed in such a way that 32 threads will run in parallel. 32 threads will always run in lockstep. They'll always run together. So even if one of the 32 threads runs slower than the remaining 31, all these 32 threads get locked up. This used to be a problem back in the day, but now these issues are sort of reduced. So essentially, you can write GPU code like CPU code these days, where threads that fail any step of the physics selections will exit immediately. And turns out this actually improved timing for us, though conventional wisdom would say that this should screw timing up, timing should go bonkers, but that did not happen to us. And then, so the point out here is that we learned most of these tricks from a hackathon we went to that was organized by NVIDIA. So an NVIDIA employee taught us most of this black magic out here. So, for instance, right here, like the amount of work that you assign to a GPU, you don't really go around limiting that. You just throw everything to the GPU and ask it to, and then ask the GPU to schedule the whole thing by itself. Turns out GPUs are quite smart these days and they're able to do it. And one other trick that we found out was pre-allocation of memory using by simply studying how many objects are created for a typical pileup 200 event. Because as you know, you can't really dynamically allocate memory on a GPU. Like you can't really use STL like a template library objects like vectors and so on. So by being able to pre-allocate stuff, we were able to kind of crunch it as much as possible. We were able to kind of fine-tune our occupancies, and we were able to crunch stuff. And so that reduces the memory footprint so that the GPUs can also concurrently do something else, since we can't just simply hog up all the GPUs that CMS provides us. And caches have also kind of become very smart these days. So as I told you here, GPUs don't really have a lot of caches. But again, NVIDIA has done some magic out here. So now, though they don't have a lot of caches, all these caches are now quite smart that we don't really need to worry about the fact that GPUs don't have a lot of caches anymore. So, which means on the timing front, our average time is something like 26 milliseconds per pileup 200 event. And I think to compare it with, say, running the combinatorial existing CKF software on 64 cores, that takes around 30 milliseconds. So in some sense, so we've kind of beat the baseline out here, even say cost-wise, because I think GPUs, at least in the future, we hope that they'll kind of get cheaper than they are currently, and the cost becomes comparable to a 64-core Xeon Gold processor. So on the timing front, we are doing quite good compared to existing CPU stuff. And I mean, this is not yet fully there. It's not like we've finished stuff. We've only scratched the surface. So we hope that we can kind of bring this down further to like, our hope is like to bring this down something like 12, 14 milliseconds per event. So as I told you, right? So on the physics algorithm optimizations, we still need to work on a better reconstruction of displaced tracks. And we also want to reduce the fake rates further. And then on the code optimization front, we still haven't like looked into half precision and tensor cores and things like that. And then we do have a bunch of very complicated mathematical calculations like computing arc sine inverse and hyperbolic functions and so on. So which we need to streamline. And then, as I told, there is still a lot to do on the timing front. And of course, our final target is for CMS to approve us and ultimately get into CMSSW. Yeah, so to summarize, track reconstruction challenges are getting computationally expensive. and we need to look into this sort of parallelizable algorithms. So our algorithm is a bottom-up localized algorithm that can reconstruct tracks in parallel and can be easily deployed on the GPUs. And as we showed, the GPU implementation produces competitive efficiency and fake rates, and it's also competitive with our target times.
This very energetic talk. We have time for some questions.
Yeah.
I see a lot of arms.
So slide 18. My name is Bonki from Stockholm. Here. So you have some corners for doublet and quintuplet.
Yeah.
And for those corners, you might need to know the size of the
we do know
doublet
it.
container or triplet container. And
Yeah.
how do you know the size of the container for you?
Wait, what do you mean by a container here? So you mean the amount of objects that we need to reconstruct, right? Ultimately,
Yes.
you mean the grid size?
The number of the doublets, or I mean,
That we know, right? So we have simulated events. We kind of typically know the multiplicities of every event involved, every object involved here.
But
So-
over allocated.
It's
over allocated.
Yes,
Basically, you over allocate.
we do. So we over allocate, but we're also trying to trim the amount of over allocation we do. So currently, I think we over allocate only by like 5-10%. Earlier, we used to over allocate a lot, but now we've kind of trimmed it down further by like creating different regions in the detector and saying there are more objects in say this particular region than out there, and so we trim things down and so on. So that way, we are able to bring the memory footprint down. And also we get a better idea of our grid size and the amount of threads that we need to allocate essentially. And as I told, right, we don't really need to worry about the block and thread dimensions that much anymore, because you can always just create, you can always ask the GPU to do more work than it can, and then the GPU will kind of schedule it. Since we are using like top GPUs, like in fact, most of this was done in a V100 GPU. And we tested only on B100s and A100s. And out there, things have gotten much smarter than before. Yeah.
On the same note, like a comment on the dimensionality in each of the state, but like, are we talking about tens of thousands of tablets and?
More like, I should have more like around 50,000 mini doublets. I think on the when it comes all the way to the quintuplets, it reduces because of all these constraints that we have. You see, I mean, you need to, because of all these extra physics constraints we have, ultimately, when it comes to the quintuplet front, things go down further. So there's a huge surge in multiplicity, and then the multiplicity comes down, ultimately to reconstruct only like thousands of tracks per event. Like, as you said, there are like 100,000 mini doublets being created. There are like 1 million segments being created. But then when it comes to the triplets, the number falls down to like tens of thousands. And then when it comes to the quintuplets, the number falls down to like 5,000.
What's the typical like a memory consumption in your pipeline?
It's around 1 to 1.4 GB per event. I've written it here. It's around 1 to 1.5 GB per event. So in principle, if we do things efficiently, we should be able to run like 16 events in parallel. But since we don't do things efficiently, we are only able to pull off 8 events in parallel. Yeah.
I'm Rocky from Stanford. So I just want to ask, like, how do you deal with the combinatorics? Like, you are having like so many doublets, and then there will be so many combinations. So how you are reducing them, and how
GPU
you
magic. Okay, let me elaborate. So when it comes to segments, essentially every possible segment candidate gets its own thread. So there are like 1 million threads being launched, out of which only 100,000 produce successful objects. So we don't care. We just say, okay, every possible combination gets its own GPU thread.
There was another.
Like the 16, how do you define your fake rates?
Fake rates defined as the number of fake objects divided by the number of total objects produced.
But the fake, okay, since you have a cut on the PT, you have a fit on your candidates?
Yeah. Oh, you mean the PT, right? Yeah. So the PT is the PT that we measure. There's no true PT for the fake rates. It's the PT that we measure. We do a fit and we get the PT.
So and it's really the same order made than the Kalman filter? Okay, 60% take rate.
So out here, what happens is most of this comes from objects that we don't create. So for instance, the pixel line segments, we don't create these. So this is created by someone else. Like this comes from the inner detector. So we currently have a very dirty collection of those. And what we observe is, in fact, you have a backup. Let me go to the.
Sorry, are they coming still from PataTrack?
No, not yet. We don't have PataTrack. We don't have the PataTrack collection yet. Sadly, I don't have the big list. We don't have the PataTrack collection yet. We are still using a slightly older tracking interface. We hope that with PataTrack, yes, most of the fake rates will come down.
I saw a question.
When you compare the timing performance between CPU and GPU, how optimizes your CPU? So you use slot of arrays as well as SIMD.
So this CPU thing, I'm not very sure. I think
This is about 2.5 seconds on a single core.
Yeah.
Yeah. So that's.
This is the deep input from it.
That's
2.4 seconds on a single core.
But
David might confirm, but that's your usual quote, right?
That's actually not true. We just divided by 64.
Yeah.
That comes around
Because
41.
you do
And
parallel
then
events.
Slava told us that there should be some other magic number that will bring it down to 30.
use SOA as well for CPU or
Which CMS algorithm this is?
Should be the PataTrack one. Should be one of the. Should be the.
Maybe I
Should be the
can.
offline one. I don't know.
Which is the number that you asked about?
So I said 30 milliseconds, right? And that came about by doing 2416 divided by 64.
Okay, let's say the baseline number for CMS based full tracking is the full tracking is a couple of seconds, 2.2. But this is the full one.
So we got it from the DP note, right? That has a slide that says some 2411 milliseconds.
I don't recognize the DP note from here, but
DP note 202113. So this is, I don't know.
From the TDR, yes. it's
Yeah, from the TDR.
2.3 seconds for the full track. So yes, I mean for you instead this is the auto tracking.
Yeah.
Yeah, but I think the most of the time is consumed by the fitting part.
No.
I mean, I think so. This is kind of a naive lower limit in the sense that we just divided it by 64, saying 64 cores, all of them get to efficient work. Ultimately, it won't be the case that way. So I think it'll be slightly higher than this.
Anyway, tomorrow there will be some more numbers.
Okay, we
I don't
wait
want
for
to-
that. There was another question.
Yeah, maybe I missed it, but you said this is clustering in
Just
line
say
segments.
your
Oh, sorry.
name for the benefit of people on
Right.
the.
I'm Daniel, my name, at Berkeley. You said this is a kind of clustering of line segments. Maybe I missed it.
I think I've used clustering in a very loose sense of the things. It's more like linking these hits together, not like clustering in the sense of K-means clustering.
Sure, yeah. But yeah, I was just wondering how exactly you do it. Is it literally mini doublet by mini doublet? Just look up table and then they just get linked together?
So first we create the mini doublets, as I told you, and then we create the segments by saying, let's say mini doublet is in some module number 1. And then, so the lookup table for modules has been generated that says module number 1 can possibly have connections with say module 40, 41, 27, 36, and whatever, 20 such modules. And then you do basically a one-to-one lookup, and then you say this time, yeah. So that's where we essentially use the GPUs, like saying every candidate gets its own thread, let the GPUs figure it out.
Okay, I take one more question and then we move on.
Wait, maybe it's 1 or 2. Oh, no, never mind.
Florence speaking. So when you're reconstructing your quintuplets, are you able to also reconstruct some which have missing mini doublets in between?
Currently, we don't, and that's where we expect the pixel triplets to help out. Sorry, this one's to help out. No, I know what you're saying. Essentially, given that there are five layers involved and something is missing, then you're screwed.
Yeah.
So that's where we expect this to help out. And yes, that is also an avenue that we need to work on. So what happened was we in fact tried to create quintuplets with one of these missing. The combinator rigs blew up. So because essentially so these two can link with any of these two. That's how the whole thing then ends up getting devised, and then the combinator rigs blew up. So that is also something we need to look on. That will shoot up the efficiency further.
Let's thank the speaker.